Picture this, a vast, invisible sea of energy rippling through the cosmos, carrying secrets from the farthest reaches of the universe. This isn't science fiction, it's the cosmic gamma ray background, a mysterious glow of high-energy light that fills the sky, yet remains one of the greatest puzzles in modern astronomy. What causes it, where does it come from, and why, despite decades of research, do we still know so little about it? Gamma rays are the most energetic form of light in the universe, born from the most violent and extreme events, exploding stars, colliding black holes, and even the elusive whispers of dark matter. But when we look at the gamma ray background, it's not just a few bright sources we see, it's a faint, almost uniform glow that blankets the entire sky. This glow is like a cosmic fingerprint left behind by processes we're only beginning to understand. In this video, we're diving into 25 of the most baffling mysteries surrounding this gamma ray background. From the role of dark matter to the explosive power of gamma ray bursts, from the enigmatic Fermi bubbles to the strange signals coming from the heart of our galaxy, each mystery is a piece of a puzzle that could reshape our understanding of the universe. So, if you've ever wondered what's hiding in the invisible light that surrounds us, or if you're curious about the forces that shape the cosmos, stay with us. By the end of this journey, you'll not only uncover the secrets of the gamma ray background, but also see the universe in a whole new light. Let's begin. Now let's dive into the first mystery, the origin of the gamma ray background. Where does this faint, pervasive glow of high-energy light come from? Scientists have been grappling with this question for decades, and while they've proposed several theories, the answer remains elusive. One leading idea is that the gamma ray background comes from unresolved sources, countless faint gamma ray emitters scattered across the universe, too dim to detect individually but collectively creating the glow we observe. These could include distant galaxies, pulsars, or even remnants of ancient supernova. Imagine trying to pick out a single star in a crowded night sky. It's nearly impossible, but together they create the Milky Way's shimmering band. Another intriguing possibility is dark matter annihilation. Dark matter, the invisible substance that makes up most of the universe's mass, might interact with itself in ways that produce gamma rays. If dark matter particles collide and annihilate, they could release bursts of energy, contributing to the background. It's a tantalizing thought. Dark matter, the universe's greatest mystery, might hold the key to another. Then there's the idea of primordial black holes. These hypothetical objects, thought to have formed in the early universe, could be emitting gamma rays as they evaporate or interact with their surroundings. If they exist, they might be scattered throughout the cosmos, adding to the gamma ray background in ways we're only beginning to explore. Yet, despite these theories, scientists are still unsure. The gamma ray background is like a jigsaw puzzle with missing pieces. Each theory fits part of the picture, but none fully explains the whole. What's clear is that solving this mystery could unlock profound insights into the universe's most extreme phenomena and even the nature of dark matter itself. As we move forward, keep this question in mind. What hidden processes are at work shaping the invisible light that surrounds us? The answer might just change how we see the cosmos. Now let's shift our focus to the second mystery, the missing sources of gamma rays. Why are so many of these high-energy emitters still unidentified? It's a question that has puzzled scientists for years, and the answer lies in the immense challenges of detecting and pinpointing these elusive sources. One of the biggest hurdles is the sheer vastness of the universe. Gamma rays can travel billions of light years before reaching us, and along the way they can be absorbed, scattered, or distorted by cosmic structures. It's like trying to trace a single drop of water in a vast ocean. The signal gets lost in the noise. Another challenge is the resolution of our instruments. While telescopes like the Fermi Gamma Ray Space Telescope have revolutionized our ability to observe gamma rays, they still have limitations. Many gamma-ray sources are faint or located in crowded regions of the sky, making it difficult to isolate them. Imagine trying to pick out a whisper in a crowded room. It's not impossible, but it requires incredible precision. Then there's the issue of variability. Some gamma-ray sources don't emit light steadily. Instead, they flare up unpredictably, making them hard to catch in the act. These transient sources, like gamma-ray bursts or flaring active galactic nuclei, can appear and disappear in moments, leaving scientists scrambling to study them before they vanish. Despite these challenges, every unidentified source adds to the gamma-ray background, creating a faint, diffuse glow that permeates the cosmos. Each one represents a piece of the puzzle, a clue waiting to be uncovered. And as our technology improves, we're getting closer to solving this mystery. So, what could these missing sources be? They might include exotic objects like microquasars, distant star-forming galaxies, or even entirely new classes of celestial phenomena. The possibilities are as vast as the universe itself, and each discovery brings us one step closer to understanding the cosmic gamma-ray background. As we continue our journey, let's keep this question in mind. What secrets are hidden in the faint glow of these unidentified sources? The answers could reshape our understanding of the universe. Now, let's turn our attention to the third mystery, the role of dark matter in the cosmic gamma-ray background. Could this invisible, enigmatic substance be responsible for some of the gamma rays we detect? It's a tantalizing possibility that has sparked intense debate among scientists. Dark matter makes up about 85% of the universe's total mass, yet it doesn't emit, absorb, or reflect light, making it invisible to traditional telescopes. So, how could it possibly produce gamma rays? The answer lies in one of the leading theories about dark matter, the idea that it's made up of particles called weakly interacting massive particles, or WIMP. According to this theory, WIMP could occasionally collide and annihilate each other, releasing energy in the form of gamma rays. These collisions would be rare, but over the vast expanse of the universe, they could add up to a detectable signal. Imagine two ghostly particles, invisible to us, crashing together in the depths of space and creating a burst of high-energy light. But why haven't we found definitive evidence of this yet? One reason is that the gamma rays produced by dark matter would be incredibly faint, blending into the background noise of other gamma ray sources. It's like trying to hear a single note in a symphony, possible but incredibly challenging. Another complication is that dark matter is thought to be distributed in a diffuse halo around galaxies, rather than concentrated in specific regions. This means the gamma rays it produces would be spread out, making them even harder to detect. Scientists are using advanced telescopes and simulations to search for these subtle signals, but so far the evidence remains elusive. Despite the challenges, the idea that dark matter could contribute to the gamma-ray background is too compelling to ignore. If proven, it would not only solve part of the gamma-ray mystery, but also give us our first direct glimpse into the nature of dark matter itself. As we move forward, keep this question in mind. Could the faint glow of the gamma-ray background be the key to unlocking the secrets of dark matter? The answer might just change everything we know about the universe. Now, let's shift our focus to one of the most dramatic events in the universe, gamma-ray bursts. These incredibly powerful explosions are some of the brightest phenomena we've ever observed, and they might hold the key to understanding part of the cosmic gamma-ray background. Gamma-ray bursts are thought to occur when massive stars collapse into black holes or when neutron stars collide. These events release an enormous amount of energy in just a few seconds, outshining entire galaxies. But what happens after the initial burst? That's where the afterglow comes in. After the initial explosion, the burst leaves behind a fading glow that can last for days, weeks, or even months. This afterglow emits not just gamma rays, but also X-rays, visible light, and radio waves. It's like the universe's way of leaving a cosmic fingerprint, a lingering trace of the explosion's power. So how do these bursts contribute to the gamma-ray background? While individual gamma-ray bursts are rare and short-lived, their afterglows can leave a lasting imprint. Over billions of years, the combined light from countless bursts and their afterglows could add up to a faint, diffuse glow that we detect as part of the cosmic gamma-ray background. But here's the twist: not all gamma-ray bursts are the same. Some are long, lasting several seconds or even minutes, while others are short, lasting just a fraction of a second. Scientists believe these differences are tied to the type of event that caused the burst, whether it's a collapsing star or a neutron-star collision. This variety adds another layer of complexity to understanding their contribution to the gamma-ray background. Detecting and studying these bursts is no easy task. They happen randomly across the sky, and their short duration makes them difficult to catch. However, thanks to advanced telescopes and satellites, we've been able to observe hundreds of these events, giving us valuable clues about their nature and their role in the cosmic gamma-ray background. As we continue to explore this mystery, one thing is clear: gamma-ray bursts are not just spectacular cosmic fireworks. They are also potential pieces of the puzzle that could help us understand the origins of the gamma-ray background. Next, we'll dive into another fascinating feature of our universe, the Fermi bubbles. What are these massive structures, and how do they connect to the gamma-ray background? Stay tuned as we uncover more cosmic secrets. Now, let's turn our attention to one of the most intriguing structures in our galaxy, the Fermi bubbles. These enormous, balloon-like features stretch tens of thousands of light-years above and below the center of the Milky Way, and they're filled with high-energy gamma rays. But what exactly are they, and how do they fit into the puzzle of the cosmic gamma-ray background? The Fermi bubbles were first discovered in 2010 by the Fermi Gamma-Ray Space Telescope, which detected a massive, symmetrical glow of gamma rays extending from the galactic center. These bubbles are colossal, each spanning about 25,000 light-years, and they're one of the largest structures ever observed in our galaxy. Their sheer size and energy output make them impossible to ignore when studying the gamma-ray background. But what created these bubbles? That's where the mystery deepens. Scientists have proposed several theories, but none have been definitively proven. One leading idea suggests that the bubbles were formed by a massive outburst from the supermassive black hole at the center of our galaxy, Sagittarius, a star. This black hole could have unleashed a tremendous amount of energy in the past, blowing out gas and particles that now glow in gamma rays. Another theory points to a period of intense star formation near the galactic center. When massive stars are born and die in rapid succession, they can produce powerful stellar winds and supernova explosions, which might have inflated the bubbles over millions of years. The debate over their origin is far from settled, but what's clear is that the Fermi bubbles are a significant source of gamma rays. Their contribution to the gamma-ray background is substantial, and studying them could help us better understand the overall distribution of gamma rays in the universe. As we continue to explore these mysterious structures, one thing is certain: the Fermi bubbles are a reminder of just how dynamic and energetic our galaxy can be. They challenge our understanding of the Milky Way and its history, offering clues about the forces that shape the cosmos. Next, we'll venture even closer to the heart of our galaxy to explore the sixth mystery, the galactic center anomaly. Why is this region emitting so much gamma radiation, and what secrets does it hold? Stay with us as we uncover more about this cosmic enigma. Now, let's journey to the very heart of our galaxy, where an even greater mystery awaits: the galactic center anomaly. This region, located at the core of the Milky Way, is a hotbed of gamma radiation, emitting an astonishing amount of energy that has puzzled scientists for decades. But what could be causing this intense gamma-ray activity? One of the leading suspects is the supermassive black hole at the center of our galaxy, known as Sagittarius, a star. This colossal object, with a mass millions of times that of our Sun, is a powerhouse of gravitational energy. As matter spirals into the black hole, it heats up to extreme temperatures, releasing bursts of gamma rays in the process. Some scientists believe that past eruptions from Sagittarius, a star, could have left behind a lingering glow of gamma radiation, contributing to the anomaly we observe today. But the black hole isn't the only player in this cosmic drama. The galactic center is also a bustling hub of star formation, with countless stars being born and dying in rapid succession. When massive stars explode as supernova, they release enormous amounts of energy, including gamma rays. Additionally, the powerful stellar winds from young, hot stars can collide with surrounding gas and dust, creating shockwaves that produce gamma radiation. This constant cycle of stellar birth and death could be another key factor behind the gamma ray glow. Then there's the intriguing possibility of dark matter. Some researchers suggest that the galactic center might be a hotspot for dark matter interactions. If dark matter particles collide and annihilate each other, they could release gamma rays as a byproduct. While this theory is still speculative, it offers a tantalizing explanation for the excess gamma radiation observed in this region. The galactic center anomaly is a complex puzzle, with multiple factors likely contributing to its intense gamma ray emissions. By studying this region, scientists hope to uncover not only the secrets of our galaxy's core, but also clues about the nature of dark matter and the behavior of supermassive black holes. As we move forward, our next mystery takes us beyond the Milky Way to explore the extragalactic contribution to the gamma ray background. How much of this cosmic glow comes from outside our galaxy, and what does it tell us about the universe at large? Stay tuned as we continue our journey through the mysteries of the cosmic gamma ray background. Now, let's turn our gaze beyond the Milky Way and into the vast expanse of the universe. The seventh mystery of the cosmic gamma ray background takes us to the extragalactic contribution. How much of this mysterious glow originates from outside our galaxy? This question is crucial because it helps us understand not just our own cosmic neighborhood, but the entire universe. The gamma ray background isn't just a local phenomenon. A significant portion of it comes from distant galaxies, quasars, and other extragalactic sources. But pinpointing exactly how much is a challenge. One of the biggest hurdles is distinguishing between gamma rays produced within our galaxy and those coming from beyond. The Milky Way itself is a rich source of gamma radiation, from pulsars to supernova remnants, making it difficult to separate the galactic noise from the extragalactic signal. To tackle this, scientists rely on detailed observations and sophisticated models. By mapping the distribution of gamma rays across the sky, they can identify patterns that hint at their origins. For example, gamma rays from outside our galaxy tend to be more evenly distributed, while those from within the Milky Way often cluster along the galactic plane. This distinction helps researchers estimate the extragalactic contribution, but it's far from straightforward. Another challenge lies in the sheer distance of these extragalactic sources. Gamma rays traveling across billions of light-years can be absorbed or scattered by intervening matter, such as gas and dust in intergalactic space. This absorption can alter the gamma ray signal, making it harder to trace back to its origin. Additionally, some extragalactic sources, like active galactic nuclei and blazars, are incredibly variable, flaring up and fading over time. This variability adds another layer of complexity to the puzzle. Despite these challenges, scientists have made significant progress. Observations from space telescopes like the Fermi Gamma Ray Space Telescope have revealed that a substantial fraction of the gamma ray background likely comes from extragalactic sources. These findings open a window into the high-energy universe, offering clues about the behavior of distant galaxies, the growth of supermassive black holes, and even the large-scale structure of the cosmos. As we continue to unravel the mysteries of the gamma ray background, the extragalactic contribution reminds us that the universe is far more interconnected than we might imagine. The gamma rays we detect today could have traveled across billions of years, carrying with them the secrets of distant galaxies and cosmic events. Next, we'll dive into the role of active galactic nuclei, supermassive black holes at the hearts of galaxies, and how they might be shaping the gamma ray background. What makes these cosmic powerhouses such significant contributors? Let's find out as we explore the eighth mystery of the cosmic gamma ray background. Now, let's zoom in on one of the most fascinating players in the cosmic gamma ray drama, active galactic nuclei, or AN. These are the incredibly energetic cores of galaxies, powered by supermassive black holes that devour surrounding matter and unleash torrents of radiation, including gamma rays. But just how significant is their role in shaping the gamma ray background? At the heart of every active galactic nucleus lies a supermassive black hole, millions to billions of times more massive than our Sun. As gas, dust, and even stars spiral into these cosmic behemoths, they form an accretion disk, a swirling, superheated ring of material. The intense gravitational forces and friction within this disk generate enormous amounts of energy, some of which is emitted as gamma rays. But that's not all. Some AGN also produce powerful jets of particles that shoot out at nearly the speed of light, colliding with surrounding matter and producing even more gamma rays. What makes AGN particularly interesting is their sheer power. A single active galactic nucleus can outshine an entire galaxy, emitting gamma rays that travel across the universe. When we look at the gamma ray background, it's likely that a significant portion comes from these distant, luminous sources. However, not all AGN are created equal. Some are more active than others, and their gamma ray emissions can vary dramatically over time. This variability adds another layer of complexity to understanding their contribution to the gamma ray background. One of the key challenges in studying AGN is their distance. Many of these sources are billions of light years away, meaning the gamma rays we detect today were emitted when the universe was much younger. This makes AGN not just sources of gamma rays, but also cosmic time capsules offering glimpses into the early universe. By analyzing their gamma ray emissions, scientists can learn about the growth of supermassive black holes, the evolution of galaxies, and even the large-scale structure of the cosmos. Observations from space telescopes like the Fermi Gamma Ray Space Telescope have revealed that AGN are indeed major contributors to the gamma ray background. In fact, some of the brightest gamma ray sources in the sky are active galactic nuclei, but there's still much to learn. For instance, how do the properties of AGN, such as their size, activity level, and environment, influence their gamma ray emissions? And how do these emissions interact with other components of the gamma ray background, like those from star-forming galaxies or dark matter? As we continue to explore the mysteries of the gamma ray background, active galactic nuclei stand out as key players in this cosmic puzzle. Their immense power and variability make them both fascinating and challenging to study, offering a window into the high-energy processes that shape our universe. Next, we'll turn our attention to another enigmatic source of gamma rays, Blazars. What makes these distant objects some of the most powerful gamma ray emitters in the universe? Let's uncover the ninth mystery of the cosmic gamma ray background. Now, let's shift our focus to one of the most extreme and mysterious objects in the universe, Blazars. These cosmic powerhouses are a special type of active galactic nucleus, but with a twist that makes them some of the brightest gamma ray sources we've ever observed. So, what exactly sets Blazars apart, and why do they dominate certain regions of the gamma ray background? Blazars are essentially active galactic nuclei with jets of particles and radiation that happen to be pointed almost directly at Earth. Imagine a supermassive black hole at the center of a galaxy, devouring matter and spewing out jets of energy at nearly the speed of light. Normally, these jets would shoot out in random directions, but in the case of Blazars, we're looking straight down the barrel. This alignment makes them appear incredibly bright and energetic, even from billions of light years away. What makes Blazars truly unique is their ability to produce gamma rays with astonishing intensity. The particles in their jets are accelerated to such high energies that they emit gamma rays as they spiral around magnetic fields. This process, known as synchrotron radiation, is one of the key reasons Blazars shine so brightly in the gamma ray spectrum. But that's not all. As these high-energy particles collide with photons or other particles, they produce even more gamma rays through a process called inverse Compton scattering. The result, a torrent of gamma rays that can outshine entire galaxies. Blazars are also incredibly variable. Their brightness can change dramatically over days, hours, or even minutes. This variability is thought to be caused by disturbances in the jets, such as shocks or instabilities, which can amplify the gamma ray emissions. For scientists, this variability is both a blessing and a curse. On one hand, it provides clues about the inner workings of Blazars and the extreme conditions near supermassive black holes. On the other hand, it makes them unpredictable and challenging to study. When it comes to the gamma ray background, Blazars are thought to play a significant role. Observations from telescopes like the Fermi Gamma Ray Space Telescope have shown that Blazars are among the brightest and most numerous gamma ray sources in the sky. In fact, some regions of the gamma ray background are dominated by their emissions. But here's the catch: not all Blazars are the same. Some are more active than others, and their contributions to the gamma ray background can vary widely. This raises intriguing questions about how much of the background is truly shaped by these enigmatic objects. As we continue to unravel the mysteries of the gamma ray background, Blazars stand out as key players in this cosmic puzzle. Their extreme energy, variability, and alignment with Earth make them both fascinating and challenging to study. By understanding Blazars, we gain valuable insights into the high-energy processes that shape our universe and the role they play in the broader gamma ray landscape. Next, we'll explore another piece of the puzzle: the connection between cosmic rays and gamma ray emissions. How do these high-energy particles contribute to the gamma ray background, and what can they tell us about the universe? Let's dive into the 10th mystery of the cosmic gamma ray background. Now, let's turn our attention to another fascinating piece of the gamma ray puzzle: the connection between cosmic rays and gamma ray emissions. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. But how do these particles, which are invisible to our eyes, contribute to the gamma ray background we observe? The answer lies in their interactions with the interstellar medium, the vast clouds of gas and dust that fill the space between stars. When cosmic rays collide with atoms in the interstellar gas, they trigger a cascade of reactions. These collisions can produce secondary particles, including pions, which are short-lived particles that quickly decay into gamma rays. This process, known as pion decay, is one of the primary ways cosmic rays generate gamma ray emissions. It's like a cosmic domino effect. A single high-energy particle smashes into an atom, setting off a chain reaction that ultimately results in the release of gamma rays. But that's not the only way cosmic rays contribute to the gamma ray background. They can also interact with photons, the particles of light, through a process called inverse Compton scattering. In this scenario, a cosmic ray transfers some of its energy to a lower energy photon, boosting it into the gamma ray range. This process is particularly important in regions where there's a lot of starlight or radiation, such as near star-forming galaxies or active galactic nuclei. The gamma rays produced by these interactions become part of the cosmic gamma ray background, adding to the overall glow we detect from space. What's fascinating is that these gamma rays carry information about the cosmic rays that created them. By studying the gamma ray background, scientists can learn more about the origin, distribution, and behavior of cosmic rays throughout the universe. However, there's still much we don't know. For example, where do cosmic rays get their incredible energy? Some are thought to come from supernova explosions, while others might originate from more exotic sources like black holes or neutron stars. And how do they travel such vast distances without losing all their energy? These questions are at the heart of ongoing research, and the gamma-ray background provides a unique window into these mysteries. As we piece together the role of cosmic rays in the gamma-ray background, we gain a deeper understanding of the high-energy processes that shape our universe. These particles, though invisible, leave a lasting imprint on the cosmos, and their interactions with the interstellar medium are a key part of the story. Next, we'll explore another intriguing contributor to the gamma-ray background, pulsars. These rapidly spinning neutron stars are not only fascinating in their own right, but also play a significant role in the high-energy universe. Let's dive into the 11th mystery of the cosmic gamma-ray background. Now, shifting our focus to another captivating piece of the gamma-ray puzzle, let's explore the role of pulsars in the cosmic gamma-ray background. Pulsars are the remnants of massive stars that have exploded in supernova, leaving behind incredibly dense, rapidly spinning neutron stars. These cosmic lighthouses are not only mesmerizing in their own right, but also play a significant role in the high-energy universe. Pulsars are known for their rapid rotation, with some spinning hundreds of times per second. This incredible speed, combined with their intense magnetic fields, creates an environment ripe for gamma-ray production. As a pulsar spins, its magnetic field accelerates charged particles to nearly the speed of light. These particles, often electrons and positrons, then emit gamma rays as they spiral along the magnetic field lines. This process, known as synchrotron radiation, is one of the primary ways pulsars contribute to the gamma-ray background. But pulsars don't just emit gamma rays from their immediate surroundings. Their powerful magnetic fields can also create structures called pulsar wind nebulae, which are vast clouds of charged particles and radiation. These nebulae act as natural particle accelerators, boosting the energy of particles and producing gamma rays in the process. The Crab Nebula, for example, is a well-known pulsar wind nebula that emits a significant amount of gamma radiation. Another fascinating aspect of pulsars is their ability to produce gamma-ray beams. These beams are often aligned with the pulsar's magnetic poles, and as the pulsar rotates, the beams sweep across the sky like a cosmic lighthouse. If Earth happens to lie in the path of these beams, we detect them as regular pulses of gamma rays. This phenomenon is what gives pulsars their name, and it's a key way they contribute to the gamma-ray background. However, pulsars are not all the same. Some, known as millisecond pulsars, spin much faster than their younger counterparts and are thought to be particularly efficient gamma-ray emitters. These older pulsars, often found in dense star clusters, may contribute significantly to the gamma-ray background, especially in regions where many of them are concentrated. Despite their importance, pulsars are just one piece of the gamma-ray puzzle. Their emissions are intertwined with those of other sources, making it challenging to isolate their exact contribution to the background. Scientists are still working to understand how much of the gamma-ray glow we observe comes from pulsars and how their emissions vary across different regions of the sky. As we continue to unravel the mysteries of pulsars and their role in the gamma-ray background, we gain a deeper appreciation for the dynamic and energetic processes at work in our universe. These spinning neutron stars, with their powerful magnetic fields and high-energy emissions, are a testament to the incredible diversity of cosmic phenomena. Next, we'll turn our attention to another intriguing contributor to the gamma-ray background, supernova remnants. These explosive remnants of dying stars are not only dramatic in their own right, but also play a crucial role in shaping the high-energy universe. Let's dive into the 12th mystery of the cosmic gamma-ray background. Now, let's venture into the explosive aftermath of dying stars and uncover the role of supernova remnants in the cosmic gamma-ray background. When a massive star reaches the end of its life, it doesn't fade quietly, it goes out with a bang in one of the most energetic events in the universe, a supernova. These colossal explosions not only scatter the star's material across space, but also leave behind a supernova remnant, a chaotic and dynamic region that continues to influence its surroundings long after the initial blast. Supernova remnants are more than just cosmic debris, they are natural particle accelerators. As the shockwave from the explosion expands outward, it slams into the surrounding interstellar medium, creating turbulent conditions that can accelerate particles to incredibly high energies. These particles, often protons and electrons, collide with other particles or interact with magnetic fields, producing gamma rays in the process. This makes supernova remnants a significant source of gamma radiation in the universe. One of the key mechanisms by which supernova remnants produce gamma rays is through a process called inverse Compton scattering. In this process, high-energy electrons collide with lower-energy photons, such as those from starlight or the cosmic microwave background, boosting the photons to gamma-ray energies. This interaction is particularly efficient in the dense, energetic environments of supernova remnants, where particles are constantly being accelerated and colliding. Another important process is hadronic interactions, where high-energy protons collide with other protons or nuclei in the interstellar medium. These collisions produce neutral pions, which quickly decay into gamma rays. This mechanism is especially significant because it directly links cosmic rays' high-energy particles that permeate the universe to gamma-ray production. Supernova remnants are thought to be one of the primary sources of cosmic rays, making them a crucial piece of the gamma-ray puzzle. One of the most famous supernova remnants is the Crab Nebula, which we've already touched on in the context of pulsars. But the Crab Nebula is also a prime example of how supernova remnants contribute to the gamma-ray background. Its intricate structure, filled with swirling magnetic fields and high-energy particles, emits gamma rays across a wide range of energies. Observations of the Crab Nebula and other remnants like Cassiopeia and Tycho's supernova remnant have provided valuable insights into how these objects shape the gamma-ray sky. However, supernova remnants are not uniform in their gamma-ray emissions. Factors like the age of the remnant, the density of the surrounding interstellar medium, and the strength of its magnetic fields all influence how much gamma radiation it produces. Younger remnants, still dominated by the shockwave from the explosion, tend to emit more gamma rays than older ones which have expanded and cooled over time. This variability adds another layer of complexity to understanding their contribution to the gamma-ray background. Despite their importance, supernova remnants are just one piece of the cosmic gamma-ray puzzle. Their emissions are intertwined with those of other sources, such as pulsars, active galactic nuclei, and even dark matter. Scientists are still working to untangle these contributions and determine exactly how much of the gamma-ray background comes from supernova remnants. As we explore the role of supernova remnants, we gain a deeper appreciation for the interconnectedness of cosmic phenomena. These remnants, born from the explosive deaths of stars, continue to shape the universe long after their initial detonation, leaving behind a legacy of high-energy radiation that helps us unravel the mysteries of the cosmos. Next, we'll turn our attention to another enigmatic feature of the gamma-ray sky, gamma-ray halos. These mysterious structures found around certain galaxies may hold clues to some of the most profound questions in astrophysics. Let's dive into the 13th mystery of the cosmic gamma-ray background. Now, let's shift our gaze to a phenomenon that seems almost otherworldly: gamma-ray halos. These vast, glowing structures, stretching far beyond the visible boundaries of certain galaxies, are one of the most intriguing features of the gamma-ray sky. But what exactly are they, and why do they form? Gamma-ray halos are enormous regions of diffuse gamma-ray emission that surround some galaxies, particularly those with active galactic nuclei or intense star formation. Unlike the sharp, pinpoint sources of gamma rays we've discussed earlier, these halos are spread out, creating a faint but detectable glow that can extend for tens of thousands of light years. Their discovery was a surprise to astronomers as they revealed a previously unseen aspect of how galaxies interact with their surroundings. One of the leading explanations for gamma-ray halos involves cosmic rays, high-energy particles that travel through space at nearly the speed of light. In galaxies with active star formation or supermassive black holes, cosmic rays are produced in abundance. These particles don't stay confined to the galaxy. Instead, they escape into the surrounding intergalactic medium, where they interact with magnetic fields and other particles. These interactions can produce gamma rays, creating the diffuse halos we observe. Another fascinating possibility is that gamma-ray halos are linked to the winds and outflows generated by active galactic nuclei. When a supermassive black hole at the center of a galaxy feeds on surrounding material, it can launch powerful jets and winds that push material outward. These outflows carry energy and particles into the galaxy's outskirts, where they can produce gamma rays. Over time, this process can create a halo of gamma-ray emission that envelops the entire galaxy. The discovery of gamma-ray halos has opened up new questions about the role of galaxies in shaping their environments. For example, why do only some galaxies have these halos? Is it related to their activity levels, their magnetic fields, or something else entirely? Observations of galaxies like Centaurus A and M82 have provided valuable clues, but the full picture remains elusive. One of the most exciting aspects of gamma-ray halos is their potential to reveal hidden processes in the universe. For instance, they might help us understand how cosmic rays are transported across vast distances, or how galaxies influence the intergalactic medium. Some scientists even speculate that gamma-ray halos could be linked to dark matter, though this remains a topic of ongoing research. As we continue to study these enigmatic structures, we're reminded of how much we still have to learn about the universe. Gamma-ray halos are not just beautiful cosmic features, they are windows into the complex interplay of energy, particles, and magnetic fields that shape the cosmos. Next, we'll explore another layer of the gamma-ray background, its unevenness. Why isn't the gamma-ray sky uniform, and what do these variations tell us about the universe? Let's dive into the 14th mystery. Now, let's turn our attention to a curious feature of the gamma-ray sky, its unevenness. Unlike the smooth, uniform glow we might expect, the gamma-ray background is patchy, with regions of higher and lower intensity scattered across the cosmos. This unevenness, known as anisotropy, is one of the most puzzling aspects of the gamma-ray background, and it holds important clues about the sources and processes that shape it. So, why isn't the gamma-ray background uniform? The answer lies in the distribution of its sources. Gamma rays don't come from a single, evenly spread origin. Instead, they arise from a variety of objects and phenomena scattered throughout the universe. Some regions of space are packed with gamma-ray emitters, like active galactic nuclei, star-forming galaxies, or clusters of pulsars, while others are relatively quiet. This uneven distribution creates the variations we observe in the gamma-ray sky. One of the key contributors to this anisotropy is the large-scale structure of the universe. Galaxies and galaxy clusters aren't randomly scattered. They form a cosmic web with dense filaments and vast voids. This structure influences where gamma rays are produced and how they travel through space. For example, regions with a high concentration of galaxies are likely to produce more gamma rays, while voids appear dimmer in the gamma-ray sky. Another factor is the role of cosmic rays and magnetic fields. As we've seen earlier, cosmic rays can produce gamma rays when they interact with other particles or magnetic fields. These interactions aren't uniform across the universe, leading to variations in gamma-ray intensity. In some regions, strong magnetic fields might trap cosmic rays, creating hotspots of gamma-ray emission. while in others, weaker fields allow particles to escape, resulting in fainter regions. Interestingly, the anisotropy of the gamma-ray background might also reveal hidden sources. For instance, some variations could point to the presence of dark matter. If dark matter particles annihilate or decay, they could produce gamma rays, creating subtle patterns in the background. While this idea is still speculative, it highlights how studying these variations could unlock new insights into the universe's most elusive components. The study of gamma-ray anisotropy is still in its early stages, but it's already reshaping our understanding of the cosmos. By mapping these variations, scientists can trace the distribution of gamma-ray sources, probe the large-scale structure of the universe, and even test theories about dark matter and cosmic rays. Each patch of the gamma-ray sky tells a story, and together they form a mosaic of the universe's most energetic processes. As we continue to explore the gamma-ray background, we're reminded that even the faintest glows can hold profound secrets. The unevenness of the gamma-ray sky isn't just a curiosity. It's a window into the dynamic, interconnected nature of the universe. Next, we'll shift our focus to another fascinating contributor to the gamma-ray background: star-forming galaxies. How do these bustling cosmic nurseries produce gamma rays, and what role do they play in shaping the gamma-ray sky? Let's find out. Now, let's journey into the heart of some of the universe's most vibrant and energetic regions: star-forming galaxies. These cosmic nurseries, brimming with newborn stars, are not just spectacular to observe. They also play a surprising role in shaping the gamma-ray background. But how exactly do these bustling galaxies contribute to the gamma-ray sky? The answer lies in the intense processes that accompany star formation. When stars are born, they don't come quietly. The birth of a star is a violent, energetic event, often accompanied by powerful stellar winds, supernova explosions, and the acceleration of cosmic rays. These cosmic rays, as we've discussed earlier, are key players in the production of gamma rays. When they collide with interstellar gas or magnetic fields, they generate high-energy gamma-ray emissions. In star-forming galaxies, this process happens on a massive scale, making them significant contributors to the gamma-ray background. One of the most fascinating aspects of star-forming galaxies is their sheer productivity. In regions where stars are forming at a rapid pace, known as starburst galaxies, the rate of supernova and cosmic ray production is exceptionally high. This means these galaxies can produce gamma rays in abundance, creating bright patches in the gamma-ray sky. For example, galaxies like Messier 82, known for its intense star formation, are some of the brightest gamma-ray sources in the universe. But it's not just the stars themselves that matter. The environment within star-forming galaxies also plays a crucial role. Dense clouds of gas and dust, which serve as the raw material for new stars, can also act as cosmic ray accelerators. As these particles zip through the galaxy, they interact with the surrounding material, producing gamma rays in the process. This means that even the quieter, less extreme star-forming galaxies contribute to the gamma-ray background, albeit on a smaller scale. Interestingly, the gamma rays produced by star-forming galaxies can also tell us about the conditions within these cosmic nurseries. By studying the energy and distribution of these gamma rays, scientists can infer details about the rate of star formation, the density of interstellar gas, and even the strength of magnetic fields. This makes gamma-ray observations a powerful tool for understanding the inner workings of these dynamic galaxies. However, the story doesn't end there. Star-forming galaxies are also linked to another cosmic mystery: the role of supermassive black holes. In some cases, the same galaxies that are forming stars at a rapid pace also host active galactic nuclei, where supermassive black holes are devouring matter and spewing out energy. This combination of star formation and black hole activity can create a complex interplay of gamma-ray emissions, further enriching the gamma-ray background. As we piece together the contributions of star-forming galaxies, we begin to see how interconnected the universe truly is. These galaxies, with their ceaseless activity and explosive energy, are not just building blocks of the cosmos, they are also key players in the gamma-ray story. By studying their emissions, we gain a deeper understanding of the processes that shape our universe, from the birth of stars to the behavior of cosmic rays. Next, we'll explore another intriguing aspect of the gamma-ray background, the mystery of gamma-ray absorption. Why do some gamma rays vanish before reaching us, and what does this tell us about the universe's hidden structures? Let's dive in. Now, let's turn our attention to a phenomenon that adds another layer of intrigue to the gamma-ray background, the mystery of gamma-ray absorption. Why do some gamma rays, despite their incredible energy, vanish before they ever reach us? The answer lies in the vast and often invisible structures that fill the cosmos, the interstellar and intergalactic medium. As gamma rays travel across the universe, they don't always have a clear path. The space between stars and galaxies isn't empty. It's filled with gas, dust, and other particles that can absorb or scatter these high-energy photons. This interstellar medium, made up of hydrogen, helium, and heavier elements, acts like a cosmic filter, soaking up gamma rays before they can reach our detectors. The denser the medium, the more likely it is to absorb these energetic particles, creating gaps or shadows in the gamma-ray sky. But the story doesn't stop there. Beyond our galaxy, the intergalactic medium, the sparse gas and dust that fills the space between galaxies, also plays a role. While it's far less dense than the interstellar medium, its vast scale means it can still have a significant impact on gamma-ray absorption. In fact, the intergalactic medium is thought to be one of the primary reasons why some gamma rays from distant sources never make it to Earth. This absorption process can even reveal hidden details about the structure and composition of the universe itself. One of the most fascinating aspects of gamma-ray absorption is how it can act as a cosmic detective tool. By studying which gamma rays are absorbed and which make it through, scientists can map out the distribution of matter in the universe. For example, gamma rays that pass through dense clouds of gas or dust leave behind a unique signature, allowing researchers to infer the properties of these otherwise invisible structures. This makes gamma-ray absorption not just a mystery to solve, but also a powerful tool for exploring the hidden architecture of the cosmos. Interestingly, the absorption of gamma rays isn't uniform. Some regions of space are more effective at absorbing these high-energy photons than others, creating variations in the gamma-ray background. These variations can tell us about the density and temperature of the interstellar and intergalactic medium, as well as the presence of magnetic fields and other cosmic phenomena. In this way, gamma-ray absorption provides a window into the complex and dynamic nature of the universe. As we continue to unravel the mystery of gamma-ray absorption, we gain a deeper understanding of the forces that shape our universe. From the dense clouds of gas within galaxies to the sparse expanse of the intergalactic medium, these invisible structures play a crucial role in determining what we see and what we don't see in the gamma-ray sky. By studying these processes, we not only solve a cosmic puzzle, but also uncover new insights into the fabric of the universe itself. Next, we'll shift our focus to another enigmatic contributor to the gamma-ray background, the role of neutron stars. How do these incredibly dense remnants of supernova produce gamma rays, and what do they reveal about the universe's most extreme environments? Let's explore. Now, let's venture into the realm of one of the universe's most extreme objects, neutron stars. These incredibly dense remnants of supernova are not only fascinating in their own right, but also play a significant role in shaping the gamma-ray background. But how exactly do these stellar corpses produce gamma rays, and what do they tell us about the universe's most extreme environments? Neutron stars are born from the explosive deaths of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, It collapses under its own gravity, triggering a supernova. What remains is a neutron star, a city-sized object packing more mass than the Sun into a sphere only about 12 miles across. This extreme density means that a single teaspoon of neutron star material would weigh billions of tons on Earth. But it's not just their density that makes neutron stars remarkable. Their magnetic fields are equally mind-boggling. Some neutron stars, known as magnetars, have magnetic fields trillions of times stronger than Earth's, making them the most powerful magnets in the universe. These intense magnetic fields, combined with the rapid rotation of neutron stars, create the perfect conditions for gamma-ray production. As neutron stars spin, their magnetic fields accelerate charged particles to nearly the speed of light. When these particles collide with the star's surface or interact with its magnetic field, they emit gamma rays. In some cases, neutron stars produce gamma-ray bursts, short, intense flashes of gamma radiation that can outshine entire galaxies for a brief moment. These bursts are some of the most energetic events in the universe, and they contribute significantly to the gamma-ray background. But neutron stars don't just produce gamma rays in bursts. Many of them emit steady streams of gamma radiation, especially those known as pulsars. Pulsars are neutron stars that beam radiation from their magnetic poles, and as they rotate, these beams sweep across the sky like cosmic lighthouses. When one of these beams points toward Earth, we detect a pulse of gamma rays. Over time, the combined emissions from countless pulsars add to the diffuse gamma ray background, creating a faint but persistent glow that permeates the universe. What makes neutron stars particularly intriguing is how they serve as natural laboratories for studying extreme physics. The conditions on and around neutron stars are so extreme that they allow scientists to test theories about matter, gravity, and magnetic fields in ways that would be impossible on Earth. For example, the behavior of matter at such high densities challenges our understanding of nuclear physics, while the intense magnetic fields provide insights into the fundamental forces of nature. By studying the gamma rays emitted by neutron stars, researchers can probe these extreme environments and uncover new details about the laws that govern the universe. As we continue to explore the role of neutron stars in the gamma ray background, we gain a deeper appreciation for their impact on the cosmos. These stellar remnants are not just relics of the past, they are active participants in shaping the universe's high-energy landscape. From their explosive births to their steady emissions, neutron stars remind us that even in the cold, dark reaches of space, there is no shortage of wonder and mystery. Next, we'll turn our attention to another intriguing aspect of the gamma-ray background, the mystery of gamma-ray variability. Why do some gamma-ray sources flicker and change in brightness, and what can these fluctuations tell us about the universe? Let's find out. Now, let's shift our focus to a fascinating puzzle that has left scientists scratching their heads, the mystery of gamma-ray variability. Why do some gamma-ray sources flicker, dim, or brighten over time? This variability isn't just a cosmic quirk, it holds important clues about the nature of these sources and their role in shaping the gamma-ray background. Gamma-ray variability can occur on timescales ranging from milliseconds to years, and it's observed in a variety of cosmic objects. For instance, active galactic nuclei, or AN, are known to exhibit dramatic changes in gamma-ray brightness. These supermassive black holes, located at the centers of galaxies, can produce jets of particles that emit gamma rays. When the activity in these jets fluctuates, so does the gamma-ray output. Similarly, Blazars, a type of AGN with jets pointed directly at Earth, can show rapid and unpredictable changes in gamma-ray intensity. But it's not just AGNs that display this behavior. Gamma-ray bursts, those incredibly powerful explosions we've discussed earlier, also exhibit variability. These bursts can brighten and fade within seconds, leaving behind afterglows that change in brightness over hours or days. Even pulsars, the rapidly spinning neutron stars, can show variations in their gamma-ray emissions, though these changes are often more subtle and periodic. So, what causes this variability? The answer lies in the complex processes happening within these sources. For AGNs and Blazars, changes in the accretion of matter onto the black hole or instabilities in the jets can lead to fluctuations in gamma-ray production. In gamma-ray bursts, the variability is often tied to the chaotic nature of the explosion itself, as well as the interaction of the burst with its surrounding environment. And for pulsars, variations can arise from changes in the star's magnetic field or the alignment of its beams relative to Earth. Understanding gamma-ray variability isn't just about solving a cosmic puzzle, it's about piecing together the broader picture of the gamma-ray background. By studying how and why these sources change in brightness, scientists can gain insights into the physical processes driving them. For example, rapid variability in AGNs might reveal details about the structure of their jets, while changes in gamma-ray bursts could shed light on the dynamics of stellar explosions. Even the subtle variations in pulsars can provide clues about the extreme conditions on and around these dense stellar remnants. Moreover, variability helps astronomers distinguish between different types of gamma-ray sources. A source that flickers rapidly might be identified as a blazar, while one that shows slower, more regular changes could be a pulsar. This ability to classify sources based on their variability is crucial for mapping the gamma-ray sky and understanding how each type of source contributes to the overall background. As we continue to explore the mystery of gamma-ray variability, we uncover not just the secrets of individual sources, but also the intricate web of processes that shape the universe's high-energy landscape. These flickering beacons of light remind us that the cosmos is anything but static. It's a dynamic, ever-changing tapestry of events and phenomena. Next, we'll delve into another intriguing aspect of the gamma-ray background, the role of cosmic magnetic fields. How do these invisible forces influence gamma-ray emissions, and what do they reveal about the universe's hidden structures? Let's find out. Now, let's turn our attention to another invisible yet powerful force shaping the gamma-ray universe, cosmic magnetic fields. These vast, unseen networks of magnetic energy stretch across galaxies and even between them, influencing everything from the movement of particles to the emission of gamma rays. But how exactly do these magnetic fields impact the gamma-ray background, and what secrets do they hold about the universe's hidden structures? Cosmic magnetic fields are like the invisible threads weaving through the fabric of space. They can guide and accelerate charged particles such as electrons and protons to incredibly high speeds. When these particles collide with other matter or radiation, they produce gamma rays. This means that magnetic fields don't just passively exist, they actively shape the gamma-ray emissions we observe. For example, in supernova remnants, magnetic fields play a crucial role in accelerating particles to near light speeds, which then produce gamma rays as they interact with their surroundings. But the influence of magnetic fields goes beyond individual sources. They also affect how gamma rays travel through space. Magnetic fields can bend the paths of charged particles, altering the direction and intensity of gamma-ray emissions. This bending, known as deflection, can make it challenging for astronomers to trace gamma rays back to their original sources. In some cases, magnetic fields can even scatter gamma rays, creating a diffuse glow that contributes to the overall gamma-ray background. One of the most intriguing aspects of cosmic magnetic fields is their role in shaping the large-scale structure of the universe. In galaxy clusters, for instance, magnetic fields can stretch across millions of light-years, influencing the distribution of gamma rays emitted by high-energy processes within the cluster. These fields can also amplify or suppress gamma-ray emissions depending on their strength and orientation, adding another layer of complexity to the gamma-ray background. Another fascinating area of study is the connection between magnetic fields and dark matter. Some theories suggest that dark matter particles could interact with magnetic fields, producing gamma rays as a byproduct. While this remains speculative, it highlights the potential for magnetic fields to serve as a bridge between the visible and invisible components of the universe. By studying how magnetic fields influence gamma ray emissions, scientists might uncover clues about the nature of dark matter itself. Understanding cosmic magnetic fields is no easy task. They are incredibly difficult to measure directly, as they don't emit light or other forms of radiation we can easily detect. Instead, astronomers rely on indirect methods, such as observing the polarization of light or the behavior of charged particles, to infer the presence and strength of these fields. Despite these challenges, advances in technology and observational techniques are gradually revealing the intricate role magnetic fields play in the gamma-ray universe. As we piece together the puzzle of cosmic magnetic fields, we gain a deeper appreciation for their role in shaping the gamma-ray background. These invisible forces are not just passive observers, they are active participants in the high-energy drama of the cosmos. By unraveling their mysteries, we move closer to understanding the full picture of the gamma-ray sky and the dynamic processes that govern it. Next, we'll explore another captivating mystery, gamma-ray echoes. What are these cosmic reverberations, and how do they help us uncover hidden sources of gamma rays in the universe? Let's dive in. Now, let's shift our focus to a phenomenon that sounds almost like a cosmic whisper, gamma-ray echoes. These mysterious reverberations are not just fascinating, they could hold the key to uncovering hidden sources of gamma rays scattered across the universe. But what exactly are gamma-ray echoes and how do they form? Imagine a powerful burst of gamma rays exploding from a distant source, like a supernova or a gamma-ray burst. As these high-energy photons travel through space, they can interact with clouds of gas, dust, or even magnetic fields. When this happens, some of the gamma rays scatter, bouncing off these cosmic obstacles and creating a delayed signal that reaches us later than the original burst. These delayed signals are what we call gamma-ray echoes. One of the most intriguing aspects of gamma-ray echoes is their ability to act like cosmic detectives. By analyzing the timing and intensity of these echoes, scientists can trace the path of the original gamma rays and identify the structures they encountered along the way. This means that echoes can reveal the presence of otherwise invisible objects, such as dense gas clouds or even remnants of ancient stellar explosions, that lie between us and the source of the gamma rays. But gamma-ray echoes aren't just about uncovering hidden objects, they also provide a unique way to study the environments around gamma-ray sources. For example, if a gamma-ray burst occurs near a black hole or a dense star cluster, the echoes can carry information about the conditions in that region. This includes details about the density of the surrounding material, the strength of magnetic fields, and even the history of high-energy events in that area. One of the challenges in studying gamma-ray echoes is their faintness. Unlike the original gamma-ray bursts, which are incredibly bright, echoes are much dimmer and harder to detect. This requires highly sensitive instruments and precise timing to distinguish them from the background noise of the gamma-ray sky. However, advancements in technology, such as the Fermi Gamma-Ray Space Telescope, are making it increasingly possible to detect and analyze these subtle signals. What makes gamma-ray echoes even more exciting is their potential to reveal sources that have long since faded or disappeared. For instance, a gamma-ray burst that occurred millions of years ago might leave behind echoes that we can still detect today. By studying these echoes, astronomers can piece together the history of high-energy events in the universe, shedding light on how galaxies, black holes, and other cosmic structures have evolved over time. As we continue to explore the mystery of gamma-ray echoes, we open a new window into the hidden corners of the universe. These faint signals remind us that even the most fleeting events in the cosmos can leave a lasting imprint waiting to be discovered. By listening to these cosmic whispers, we gain a deeper understanding of the dynamic and ever-changing nature of the gamma-ray universe. Next, we'll turn our attention to another enigmatic puzzle: primordial black holes. Could these ancient remnants from the early universe be responsible for some of the gamma-ray emissions we observe? Let's find out. Now, let's venture into one of the most speculative yet captivating mysteries of the gamma-ray universe: primordial black holes. These hypothetical objects, thought to have formed in the earliest moments of the universe, could hold the key to understanding some of the gamma-ray emissions we observe today. But what exactly are primordial black holes, and how might they contribute to the cosmic gamma-ray background? Primordial black holes are unlike the black holes we're more familiar with, such as those formed from collapsing stars. Instead, they are believed to have originated from tiny, dense fluctuations in the fabric of space-time during the universe's infancy. These fluctuations, if dense enough, could have collapsed under their own gravity, creating black holes with masses ranging from as small as an atom to as large as a star. Because they formed so early in the universe's history, primordial black holes could be scattered throughout the cosmos, lurking in the shadows and potentially influencing the gamma-ray background in ways we're only beginning to understand. One of the most intriguing possibilities is that these ancient black holes could be emitting gamma rays through a process known as Hawking radiation. According to theoretical physicist Stephen Hawking, black holes aren't entirely black. They can slowly lose mass and energy by emitting particles, including gamma rays, over incredibly long timescales. For primordial black holes, especially those with smaller masses, this radiation could be significant enough to contribute to the gamma-ray background we detect today. If this is the case, these elusive objects might be hiding in plain sight, their faint gamma-ray signatures blending into the cosmic background, but the mystery doesn't end there. Primordial black holes could also interact with their surroundings in ways that produce gamma rays. For example, if one of these black holes were to pass through a dense cloud of gas or dust, the intense gravitational forces could heat the material, causing it to emit gamma rays. Alternatively, collisions between primordial black holes and other objects, such as neutron stars or even other black holes, could release bursts of gamma radiation. These interactions, though rare, could leave behind detectable traces in the gamma-ray background. Detecting primordial black holes, however, is no easy task. Their small size and faint emissions make them incredibly difficult to observe directly. Scientists rely on indirect methods, such as searching for the unique gamma-ray signatures predicted by Hawking radiation or looking for gravitational effects on nearby objects. So far, no definitive evidence of primordial black holes has been found, but their potential existence continues to inspire research and speculation. If primordial black holes do exist, their impact on the gamma-ray background could be profound. They might help explain some of the unresolved gamma-ray emissions that puzzle astronomers, offering a glimpse into the universe's earliest moments. At the same time, their discovery would revolutionize our understanding of black holes, dark matter, and the evolution of the cosmos itself. As we explore the role of primordial black holes in the gamma-ray universe, we're reminded of how much remains to be discovered. These ancient relics, if they exist, could be hiding secrets about the universe's origins and its most mysterious phenomena. By continuing to search for their elusive signals, we inch closer to unraveling one of the greatest cosmic mysteries of all. Next, we'll turn our attention to another fascinating puzzle: gamma-ray shadows. What are these cosmic silhouettes, and what can they tell us about the structures hidden in the universe? Let's dive in. Now, let's shift our focus to a phenomenon that acts like a cosmic silhouette: gamma-ray shadows. These intriguing features are not just empty patches in the sky, but windows into the hidden structures of the universe. So, what exactly are gamma-ray shadows, and why do they matter? Gamma-ray shadows form when dense cosmic structures, like massive galaxies or clusters of galaxies, block the path of gamma rays traveling from distant sources. Imagine holding your hand in front of a flashlight. The shadow it casts reveals the shape of your hand. Similarly, when gamma rays encounter these massive objects, they're absorbed or scattered, creating a shadow in the gamma ray sky. These shadows are not just random voids, they're precise indicators of the presence and properties of the objects casting them. But here's where it gets fascinating. Gamma ray shadows aren't just about what's blocking the light, they're also about what's behind it. By studying these shadows, scientists can learn about the nature of the gamma ray sources themselves, as well as the properties of the objects in between. For example, the size, shape, and density of the shadow can reveal details about the structure of the intervening galaxy or cluster, such as its distribution of gas, dust, and even dark matter. One of the most exciting aspects of gamma ray shadows is their ability to probe the universe on a grand scale. Because gamma rays travel such vast distances, the shadows they cast can provide insights into the large-scale structure of the cosmos. They can help map out the distribution of matter across the universe, from individual galaxies to the cosmic web, the vast network of filaments and voids that make up the universe's skeleton. In this way, gamma ray shadows act like cosmic X-rays, revealing the hidden anatomy of the universe. But detecting these shadows is no simple task. Gamma rays are incredibly high energy, and the objects casting the shadows are often faint or diffuse. Scientists rely on sensitive instruments like the Fermi Gamma Ray Space Telescope to capture these subtle features. By carefully analyzing the data, they can piece together the story of what's happening in these shadowy regions of the sky. What's more, gamma ray shadows can also tell us about the nature of gamma ray sources themselves. For instance, if a shadow appears sharper or more defined, it might indicate that the source is compact, like a pulsar or a blazar. On the other hand, a more diffuse shadow could suggest a more extended source, such as a star-forming galaxy or a supernova remnant. By studying these variations, scientists can better understand the diversity of gamma ray sources and their contributions to the cosmic gamma ray background. As we unravel the mystery of gamma ray shadows, we gain a deeper appreciation for the intricate interplay of light and matter in the universe. These cosmic silhouettes are more than just shadows, they're clues to the hidden structures and processes that shape our cosmos. By continuing to study them, we move closer to understanding the grand tapestry of the universe and our place within it. Next, we'll explore another piece of the gamma ray puzzle, the role of intergalactic gas. How does this diffuse material contribute to the gamma ray background, and what secrets does it hold about the universe's evolution? Let's find out. Now, let's turn our attention to the vast, invisible ocean that fills the spaces between galaxies' intergalactic gas. This diffuse material, often overlooked, plays a surprisingly significant role in shaping the cosmic gamma ray background. But how exactly does something so faint and spread out contribute to such high-energy phenomena? Intergalactic gas is not just empty space. It's a dynamic medium teeming with particles, including protons, electrons, and even the occasional heavier elements. When cosmic rays, high-energy particles traveling through space collide with these gas particles, the interactions can produce gamma rays. This process, known as hadronic interaction, occurs when cosmic rays strike protons or other nuclei in the gas, creating secondary particles that decay into gamma rays. These gamma rays then join the cosmic background, adding to the overall glow we observe. But the story doesn't end there. Intergalactic gas also plays a role in shaping the gamma ray background through another mechanism, inverse Compton scattering. In this process, high-energy electrons within the gas collide with lower-energy photons, such as those from the cosmic microwave background. These collisions boost the photons to gamma-ray energies, effectively converting them into gamma rays. This means that even the faintest light in the universe can be transformed into the most energetic radiation, thanks to the presence of intergalactic gas. One of the most intriguing aspects of intergalactic gas is its distribution. It's not spread evenly across the universe, but instead forms a complex web of filaments and voids, often referred to as the cosmic web. This structure is shaped by gravity, with dense regions pulling in gas to form galaxies and clusters, while the voids remain relatively empty. The gamma rays produced in these regions can tell us a lot about the gas's density, temperature, and composition, offering clues about the universe's evolution over billions of years. Studying intergalactic gas is no easy task, though, because it's so diffuse it doesn't emit much light on its own, making it difficult to observe directly. Instead, scientists rely on indirect methods, such as analyzing the absorption lines in the light from distant quasars, or using gamma-ray observations to trace the gas's influence. By combining these techniques, researchers can piece together a picture of how intergalactic gas contributes to the gamma-ray background, and by extension, the universe's history. What's more, intergalactic gas isn't just a passive player in the cosmic drama. It's also a key ingredient in the formation of galaxies and the large-scale structure of the universe. As gas flows into galaxies, it fuels star formation and feeds supermassive black holes, which in turn can produce their own gamma rays. This interplay between gas, galaxies, and gamma rays creates a feedback loop that shapes the universe on the grandest scales. As we explore the role of intergalactic gas, we uncover yet another layer of the gamma-ray background's complexity. This diffuse material, often hidden in plain sight, is a vital piece of the puzzle, connecting the smallest particles to the largest structures in the cosmos. By understanding its contributions, we gain a deeper appreciation for the intricate processes that shape our universe. Next, we'll delve into the mystery of gamma-ray time delays. Why do some gamma rays arrive at different times, and what can these delays tell us about the universe's structure and history? Let's find out. Now, let's shift our focus to a fascinating puzzle that has left scientists scratching their heads: gamma ray time delays. Why do some gamma rays originating from the same event arrive at Earth at different times? This phenomenon isn't just a quirk of nature. It holds profound implications for our understanding of the gamma-ray background and the universe itself. Gamma rays, despite being the fastest form of light, don't always travel in a straight line or at a constant speed. When they journey across the cosmos, they encounter various obstacles and influences that can alter their path and timing. One major factor is the presence of cosmic structures such as galaxies, galaxy clusters, and even the vast cosmic web of intergalactic gas we just discussed. These structures can bend and delay gamma rays through a process called gravitational lensing, where the immense gravity of massive objects warps the fabric of spacetime, effectively creating a cosmic detour for the gamma rays. But gravitational lensing isn't the only culprit. Gamma rays can also be delayed by interactions with magnetic fields scattered throughout the universe. These fields, though invisible, are incredibly powerful and can deflect gamma rays, causing them to take longer, more winding paths to reach us. This effect is particularly noticeable in regions with strong magnetic fields, such as those near pulsars or within the turbulent environments of active galactic nuclei. Another intriguing possibility is that gamma-ray time delays might be linked to the very nature of spacetime itself. Some theories suggest that spacetime may not be as smooth as we once thought. Instead, it could have a granular, foamy texture at extremely small scales, a concept known as quantum foam. If this is true, gamma rays traveling through this foamy spacetime could experience slight delays as they navigate the tiny fluctuations in the fabric of the universe. While this idea is still speculative, it opens up exciting avenues for exploring the fundamental nature of reality. So, what do these time delays mean for the gamma-ray background? For one, they provide a unique way to map the universe's structure. By analyzing the arrival times of gamma rays from distant sources, scientists can infer the distribution of matter along their paths, including dark matter, which doesn't emit light but exerts gravitational influence. This technique, known as gamma-ray tomography, could revolutionize our understanding of the cosmic web and the hidden components of the universe. Moreover, gamma-ray time delays offer clues about the origins of these high-energy photons. If gamma rays from the same event arrive at different times, it suggests that they were produced through different mechanisms or traveled through varying environments. This information can help astronomers piece together the complex processes that generate gamma rays, from the explosive deaths of massive stars to the violent outbursts of supermassive black holes. As we unravel the mystery of gamma-ray time delays, we gain not only a deeper understanding of the gamma-ray background, but also a new tool for probing the universe's most elusive secrets. These delays, once seen as mere curiosities, are now recognized as vital clues in our quest to decode the cosmos. Next, we'll explore the final mystery in our journey, the future of gamma-ray astronomy. What groundbreaking discoveries await us as we continue to peer into the high-energy universe? Let's find out. Now, as we step into the final chapter of our exploration, let's turn our gaze toward the horizon of discovery, the future of gamma-ray astronomy. What lies ahead in our quest to unravel the secrets of the gamma-ray background? The answer lies in the cutting-edge missions and technologies poised to revolutionize our understanding of the high-energy universe. One of the most exciting developments on the horizon is the launch of next-generation gamma-ray telescopes. These advanced instruments, like the proposed Advanced Telescope for High-Energy Astrophysics, or Athena, promise to deliver unprecedented sensitivity and resolution. With these tools, scientists will be able to detect fainter gamma-ray sources, map the gamma-ray background with greater precision, and uncover hidden structures in the cosmos that have eluded us until now. But it's not just about building bigger telescopes. Future missions are also focusing on multi-messenger astronomy, a groundbreaking approach that combines gamma-ray observations with data from other cosmic messengers, such as gravitational waves, neutrinos, and cosmic rays. By piecing together these different signals, astronomers can gain a more complete picture of the universe's most violent and energetic events, from colliding neutron stars to the explosive cores of distant galaxies. Another promising avenue is the development of space-based observatories designed to operate beyond Earth's atmosphere, where gamma rays can be observed without interference. Missions like the Compton Spectrometer and Imager, or COSI, aim to study the gamma-ray sky with unparalleled clarity, shedding light on the origins of the gamma-ray background and the processes that shape it. Closer to home, advancements in computational power and artificial intelligence are transforming how we analyze gamma-ray data. Machine learning algorithms are being trained to sift through vast amounts of information, identifying patterns and anomalies that might otherwise go unnoticed. These tools are helping scientists uncover new gamma-ray sources, refine their models of the gamma-ray background, and even predict where the next major discoveries might occur. As we look to the future, one thing is certain: the mysteries of the gamma-ray background are far from solved. Each new observation, each technological breakthrough, brings us closer to understanding the forces that shape our universe. From the enigmatic glow of the gamma-ray background to the explosive events that light up the cosmos, the journey of discovery is just beginning. So, what will the next decade of gamma-ray astronomy reveal? Will we finally uncover the role of dark matter in gamma-ray emissions? Could we detect gamma rays from the earliest moments of the universe, offering a glimpse into the birth of spacetime itself? The possibilities are as vast as the cosmos, and the answers await us in the stars. Thank you for joining us on this journey through the 25 mysteries of the cosmic gamma-ray background. If you enjoyed this exploration of the universe's hidden wonders, don't forget to like, subscribe, and hit the notification bell for more deep dives into the mysteries of space. Until next time, keep looking up. The cosmos has so much more to reveal. As we bring our journey through the 25 mysteries of the cosmic gamma-ray background to a close, it's worth reflecting on just how much these enigmatic signals reveal about the universe. From the origins of the gamma-ray background to the role of dark matter, pulsars, and even the explosive power of gamma-ray bursts, each mystery offers a unique window into the high-energy cosmos. These puzzles remind us that the universe is far more complex and dynamic than we often imagine, filled with phenomena that challenge our understanding and push the boundaries of science. The gamma-ray background isn't just a faint glow in the sky, it's a cosmic tapestry woven from the most extreme events in the universe. It tells the story of colliding neutron stars, the birth and death of stars, the invisible influence of dark matter, and the relentless activity of supermassive black holes. By studying this background, we're not just solving scientific riddles, we're piecing together the history of the universe itself, but the story doesn't end here. Every discovery raises new questions, and every answer brings us closer to understanding the forces that shape our cosmos. What lies beyond the gamma-ray background? Could it hold clues to the nature of dark matter or the earliest moments of the Big Bang? The answers are out there, waiting to be uncovered by the next generation of telescopes, missions, and brilliant minds. Thank you for joining us on this exploration of the cosmic gamma-ray background. If you've enjoyed unraveling these mysteries with us, don't forget to like, subscribe, and hit the notification bell so you never miss a deep dive into the wonders of space. The universe is full of secrets, and together we can uncover them one mystery at a time. Until next time, keep looking up. The stars have so much more to